Can't find the stupid record button. All right. So here's where we're going today. Right. We kind of got a little bit of a crash course in some of this on Friday. We did the lab, but we're going to fill in some blanks. Make sure you guys are.
Hello, Professor. Before we start for today, I have a quick question.
Yes, ma'am.
I'm taking a Spanish class 132, but the time is overlapping exact with your time. So your classes are required attendance because you both classes start 11:30 Monday to Thursday, and then end at 12:30. So I'm just curious, like, how is that possible?
Well, so here's what happens. Once upon a time, before the pandemic hit, this class was originally assigned to be an on-campus, non-online class. And at that time, the timestamp for this class was 11:30 to 1. Now, when the COVID thing shifted everything to online, they went ahead and shifted the schedule for this class to also be online. And you'll notice, like, if you look on your schedule, or like on Genzabar, the time listing for this class is something stupid, like from 1 a.m. to 1:01 a.m. or something crazy like that. That's just how they deal with online courses. There's not a scheduled time for it. And you don't have to attend class. You are not required to be in class. Your attendance for an online course has to do with your interactions on campus. If you've submitted assignments, you're attending. That's how that works.
Okay.
However, at some point, because I don't have a huge backlog of previously produced videos for all this stuff, I have to record things anyway. And so I also don't like talking to an empty room if I can avoid it. So, when I had to choose a time to record like class videos, I just chose the same time we had originally. And you guys are encouraged and invited to be here for that. So you can ask questions and answer my questions, and I can kind of gauge the room a little bit about how well we understand stuff. So if your other class meets at this time, go to your other class. You can always watch the video later and come see me during office hours. So, it's not a required thing. You don't have to be here. It might be helpful if you are. And if your other class is recording videos, maybe you can skip them sometimes and come here. I don't care. But that's what that is. So don't feel like, that's an issue. It's just because I have to do these videos at some point, and the most logical time to choose just happened to be the time that would have been the class time before anyway.
So. Okay, I'm just curious, like, when whoever set up this schedule, you should know there's another classes overlapping. In fact, the other that I'm going to is at 20%. Attendance is 20%. So
definitely go to her class. I mean, yeah, if she's taking attendance at the synchronous sessions, she should be your priority, because if you're not here for this session, I'm not docking your grade at all. Your attendance has nothing to do with your grade in my class. So
but your class is the physics that's requires so much.
I'm sorry?
Your class is of physics. Physics requires so much of
interaction. It is difficult, but I have office hours. Go to her class and then make an appointment after her class, and I can help you sort of make sense of the video. So maybe that should be your process: is go to her class, get out of her class. Usually by that time, the video for the class that I had earlier will be up. It takes a while to process them, and then I have to upload them to YouTube, and it takes a while for them to process there as well. Usually within an hour or two, that'll be up there. So what I would suggest is go to her class, get out of her class, watch the video from my class, and then if you have questions, make an appointment and come talk to me. I've got office hours every day.
Okay, I will mention this one to her, and then I do my best.
Okay.
All right. Thank you.
Yeah, you're welcome. All right. So any of you who are in that same situation, that's my advice to you. It's unfortunate that those two times overlapped. They wouldn't have if it stayed on ground, because you wouldn't have registered for both classes at the same time. if that were the case. But because things are online and stuff is weird, you know, no matter what I had chosen for this session, it probably would overlap with something. So, all right. So back to physics. So on Friday, we were dealing with the moving man. You guys hopefully had an educational time with that, and remember that's due this coming Friday. So if you haven't finished it yet, you know, take a crack at it. What I want to do today, first off, is I want to formalize something that hopefully was intuitive to you, but maybe hasn't been spelled out rigorously. And that's the difference between the average velocity and what we call the instantaneous velocity. The average velocity is the thing we talked about last week, and the instantaneous velocity is, it's like the thing that your speedometer in your car reads. And it's not entirely obvious how those two things are connected. So I want to go ahead and spell that out a little bit. So let's switch over to this. So let's imagine that I've got some object that's moving around, and if I plot out its position graph, so here's the position as a function of time, and let's do this one simply. Let's have this guy here have a position graph that looks like this. Imagine that line is straight. I can't draw a straight line to save my life. So if this is the situation, if I have an object that has a position versus time graph that looks like that, how would you characterize the motion of that object? What would you tell me about how that object is moving based solely on what you can see in that graph? No takers? So what we saw last, okay.
It goes proportionally time and position is the velocity is consistent.
Yeah, its velocity is consistent, and that's exactly correct. Because what we learned last time, remember, is that your velocity, right, was the change in position over time. And if I'm looking at one of these graphs, the thing that occurs to me is that the change in position, that's the rise of the graph. The change in time is the run of the graph. And so the rise over the run, that's a slope. And so if I'm looking at this thing here, the slope of that graph tells me the velocity of the object. Had I drawn this line to be steeper, then what would have happened is the rise over the run would have been a bigger number. That would have represented an object traveling at a larger velocity. And that's fine and dandy for things that look like this. But now let's make it more complicated. Imagine I have a different object, but this time the position graph looks something like this. Now, I know that the slope of my graph tells me the velocity of the object, but it's not immediately obvious to me what a slope even means for something that's curvy. How do I find the slope of a curvy line? And to make sense of this, what I'm going to have to do is to try breaking this down over different time intervals. So imagine that I go from time 0 up to some final time. And let's switch colors just to make this a little easier to see. So if I were to go and measure the change in position from time 0 to this time, well, at that time, where is my dude? He's right here, right? And if I did the rise over run from this time to this time, in other words, the delta x, which is this much, the delta t, which is this much, what I would get is a slope, and it would be the slope of this line right there, right? That slope right there is what I would get for the velocity if I measure it over the full period of 0 to whatever that time is.
Wait, so what was the first graph again?
Well, the first graph is just some object that's moving with a velocity that's not changing, right? It's got, because a line has one slope the whole way, right?
Mm-hmm.
So if I was driving down the highway with my cruise control set at 50, right? I might have a position graph that looks like this, because every hour that I travel, I will have gone 50 miles. If I go for another hour, I'll go another 50 miles.
So that's position.
Yeah, these are both of these are positions. Okay. But the slope of this graph tells me the velocity. So if this was somebody whose cruise control was set at 50 miles an hour, this might be somebody's cruise control set at 60 miles an hour. Steeper slope means faster velocity.
Okay.
Right. But here, what's happening is I've got this curvy thing, and a curvy line isn't going to have the same slope at all different moments. So this might be what I see from somebody who's driving their car down the highway, but their cruise control is not set, right? They're going to maybe going faster sometimes and slower at other times. And so what I'm trying to do is to figure out, like, how would I even know what the number is on their speedometer if it keeps changing? And if I just do the rise over run trick, I would get the slope of this dotted red line, which is not the same as the purple line, right? So this right here would represent what we've been talking about as the average velocity, right? Because this is the velocity that person would have had to go from point A to point B if they were only ever allowed to have one speed the entire way. Right? If you wanted to go from here to this point here in this amount of time, but you could only have one speed the whole way, you'd have to have a velocity of whatever that slope represents here. But clearly, along this purple curve, sometimes they were doing something different than that. Sometimes they were traveling faster, other times they were traveling slower. And if I want to know what their velocity is in a particular moment, I'm going to have to think this through a little bit more carefully. And one way to think about why these two things don't match is because I'm measuring for a huge amount of time. Maybe this is like several hours, right? If you were driving from Charlotte to Raleigh and it took you a couple of hours, you're going to have different velocities during that 2 hours. And it's not going to give you a sense of what your speedometer says if all you look at is, I drove this many miles and it took me this many hours. That's not going to give you the details of what happened in between. If I want to get those details, what I'm going to have to do is take my measurement over a shorter interval of time. So what if I did this? What if instead of starting my stopwatch at time 0 and ending my stopwatch at this final time, what if I started my stopwatch a little bit later and I ended my stopwatch a little bit later? So now what's going to happen is, at this moment, where's my guy? He's right here. At the moment that I stop my stopwatch, where's my guy? He's here. So what's going to happen is, between here and here, the rise was this much, the run was this much, the velocity, the average velocity from here to here would be connecting those two things. And you'll notice that this dotted blue line is a whole lot closer to the purple line that I started with. So what's going to happen is, this would be the average velocity but this is the average velocity from the beginning to the end. This is the average velocity from this moment to this moment. So I'm taking the average over a shorter amount of time. And I get a slope that more closely matches what the purple line was actually doing. But I could do better than that still. Because why start here and stop there? Let's make these two times get even closer together. And what I can imagine happening is making that interval get closer and closer and closer and closer until my starting point and my ending point just meet. And if I did that, what would happen is, let's say at this moment right here, there's going to be a spot where I could draw a line that just barely touches the purple line. That's what we would call a tangent line. So a tangent line touches a curve at exactly one location. And if I take the slope of that tangent line, the slope of that tangent line is what we call the instantaneous velocity. Right? This is the thing that I'm reading on my speedometer at any given moment. So this is starting to get a little cluttered. Let me redraw this in a slightly less cluttered fashion. So if I've got some weird curvy position and I want to know the instantaneous velocity at a particular moment in time, what I want to do is draw a tangent line at that particular time, and I would look at the slope of that tangent line. So like if I wanted to know, like at this moment right here, what is the velocity of my object, I would go up to the curve at that point. And at that point, I would draw a tangent line. Now, for this, the tangent line would look something like that. Notice this goes up and to the right. So that's a positive slope. Right? However, if I looked at a different moment in time, let's say right here, well, at that moment, this tangent line would be almost completely flat. Well, a flat line has a slope of 0. So what that tells me is that at this moment here, my object was traveling with whatever this slope is, that speed in the positive direction. At this moment here, the guy has basically stopped. By the time I get out to here, the slope is positive again. And in fact, this is a little bit steeper than that. So it looks like here he's started moving again. Right here, very, very early on, that's the steepest the slope ever got, right? That's super steep. Which means right here, the guy's traveling really, really fast. Then he slows down, basically comes to a stop. Then he starts speeding up again. So maybe this is what you would see if you had a car that was driving down the road, came to a stop sign and slowed down, stopped for a while, then took off again. Does that make sense?
Yes.
Super easy. What if I had a position graph that looked like this? What's happening in this graph? Well, if I look at it at this moment right here, if I were to draw a tangent line at that point, it would be down and to the right. That's a negative slope. But what's happening is that negative slope, if I look a little bit later, right here, the tangent line is horizontal. This is somebody who's going in the negative direction. So maybe they're traveling to the left, but they're slowing down, and right here they come momentarily to a stop. And then a few seconds after that, now the tangent line is up and to the right. That's a positive slope. So that's somebody who's traveling to the left, they come momentarily to a stop, and they head back the direction that they originally came from. So conceptually, that's what we're doing when we talk about the instantaneous velocity. Now, usually you're not going to have to draw stupid graphs or anything like that. And in fact, if you've taken calculus, which most of my students, in spite of the fact this is a non-calculus based class, most of you guys have taken calculus, and you've certainly seen this same sort of trick before. What am I talking about here? What am I doing when I look at the slope of a tangent line? It's a derivative. So if you know what a derivative is, we're taking derivatives. We're saying that velocity is the derivative of the position. And in fact, when you guys first learned what derivatives were, the way you defined derivatives is you had some kind of function, and what you kept doing is you kept looking at the rate of change, the rise over the run, over smaller and smaller and smaller intervals, and you took the limit as that interval approached zero. Neat. If you don't know what any of that means, don't worry about it. You don't have to know, because we're doing all the calculus kind of behind the scenes, and turns into this. So that's sort of the key insight that's going to help us sort of understand instantaneous values, is we're just measuring the change over a vanishingly small amount of time. If I measure the change over a not vanishingly small amount of time, if delta t is not infinitely tiny, then this is not the instantaneous velocity, it's the average velocity. And that has its uses, but the average velocity is what you would get if you only had one slope the whole way. Neat. So we've got that concept. One thing that will help us tremendously, and you had some of these on your pre-lab for Friday, is that we could do the same trick with acceleration that we did with velocity. So for instance, if I was looking at, let's say, a position graph that looked like this. So if this was my position graph, what's the object doing? In words, what's accounting for this kind of motion?
It's accelerating in a negative way, negative direction.
It's not accelerating in the negative direction, but it is moving in the negative direction. This is like somebody traveling to the left, but because this line is straight, it's got one slope the entire way. So it's one single negative velocity the entire time. If I were to draw the velocity of this same object, its velocity graph would be at all times the same negative number. It'd be at time zero, it'd be negative something. At time 1 second, it'd be negative something. It'd be negative the whole way. So it's below zero by some amount. The steeper that is, the lower that would be. If I wanted to look at the acceleration of this object, what would the acceleration of this object be? Well, the trick for that is to remember that just like v is delta x over delta t, the definition of a is delta v over delta t. So on this graph, the rise over the run gives me the acceleration. What's the rise over run of that graph?
Zero.
Zero. So this would be a value of just flat out zero the entire time. And we saw that the other day. Hopefully. I don't want the camera stupid. There we go. So when we did the lab stuff the other day, we hopefully saw that same deal. Seriously? There we go. So we saw this same kind of deal. Because look, if I have this guy, let's have him start at something positive. Let's go to charts, actually. I'm going to have him start somewhere positive. Let's clear that. Stop it. Reset all. So we'll start that at like something like 10. Let's give him a velocity of -5 and hit play. What you will see is that we're getting exactly the behavior that we predicted, right? I've got a straight line that goes down and to the right, just like we had earlier. I have a velocity that's one value, but always below 0. And then I have an acceleration that's 0 the entire time. So what we saw was the same thing we predicted. You know, if I wanted to instead do something that looked like that parabola from before, then maybe I'll start $10. Let's give that some like a negative direction. And let's give him like, darn it, I'm not done yet. All right, let's try this again. Only this time, let's be less stupid. There we go. If I look there, then what you can see is here I have a parabola. And what's happening now is that my velocity is starting out with large and negative because the slope was originally very large and negative, but the slope is continuously getting smaller. Right here, the slope momentarily passes through 0. Then it becomes positive. That's corresponding to when it bottoms out and starts to bend back upward. However, this right here has one slope the entire time. It's a positive slope, which is why the acceleration was positive the entire time. And of course, this is what happens when I crash into the wall, which we're ignoring. So that sort of graphical interpretation is the thing that I hope that you guys are going to get good at over the course of either doing the lab, and there's a couple homework problems that deal with this as well. How do you guys feel about this? Does this make sense? I often find this is one of the places where students get really, really confused because they have a hard time sort of evaluating this sort of constantly changing thing. Okay, don't jump up at once. So now that we have this idea of instantaneous versus average set up, we're going to start solving honest to God problems. And again, you had a little bit of a taste of this on Friday, but I want to formalize this and hopefully get you guys comfortable working problems in one-dimensional kinematics. We learned on Friday they were 4 equations of motion that we can use to solve basically any problem that gets thrown our way. So those four equations of motion. What the heck? All right, I'm getting told that this meeting is going to end in 10 minutes because for some reason it's not recognizing that I'm a pro user. So I may have to kill the meeting and then restart it again. So we'll have like a 2-volume video. It did the same thing this morning, and I'm not sure what's going on with that. But let's see if we can get through this first. I'm not sure why it's not working right. So these are what we call our 4 kinematic equations. And the thing about these 4 kinematic equations is that of the 6 things that we could have to keep track of in a kinematics problem, each one of these equations is missing one vital element. And one thing that I have found like unimaginably helpful when I was first learning this stuff was when I was solving problems in that first chapter, I'd have this list of equations handy the entire time. And what I would take note of is what was missing from each equation. So this equation here that I call the position equation, it has all 6 of my kinematic variables, but it's missing a single one. It's missing the final velocity. Remember the notation. V sub 0 is initial velocity. V without a subscript is the final velocity. This equation is missing any kind of positions. There's no x's. This equation, however, nowhere in that equation does time appear. This equation, which I call the useless equation, doesn't have any mention of acceleration. And by noting what variable is missing from each of those equations, you're going to be able to figure out at a glance what it is that you have to use to solve whatever problem that you're solving. So when we go to solve problems in 1D kinematics, there is a process. And the process is the same no matter what I throw at you. All that's ever going to change is how you implement some of the steps. All right. Step 1 of every problem, draw a picture. Now, it's not that I like to draw. I suck at art. You're going to see this as the semester grows on. It's not about the drawing per se. It's because in every physics problem, you usually have this big block of words. And what you're trying to do is to sort of parse through all of those words and make sense of what's actually happening. And the picture is going to help you kind of track who's going where. So when you draw that picture, you're going to label the heck out of it. Essentially, we're going to use that picture as a supplement to our somewhat faulty short-term memory that can't keep track of all these moving parts. And it's often helpful in that picture if things are moving around, maybe you'll like draw the object in one location saying, hey, this is where it is originally, and then somewhere else you'll draw where the object ends up at a later time. So you may have the picture include your object at different locations in time so that you can keep track of where it is and when. Now, once you have done that, you're going to be able to get a physical sense of what's happening in the problem. The next step in every physics problem is we're going to choose a coordinate system for describing all this stuff. When you choose that coordinate system, we're making 2 choices. We're choosing where am I calling x equals 0? We have to pick that spot. And it doesn't matter what we pick as long as we're aware of what we picked and we're consistent with it. And the second thing we're choosing is what direction is the positive direction and what direction is the negative direction. a lot of times I'll default to right being to the positive direction and left being the negative direction, or up being positive and down being negative. But it doesn't matter. Pick whatever you like. As long as you're consistent, you'll get the right answer. So you'll choose your coordinate systems, and then you'll take inventory of what's given. Or you want to get a sense of what stuff do you know, and more importantly, what stuff do you not know? Because that's where the next step is going to come in. Once you've sort of taken stock of what information you've got and what information is missing, your third step is going to always be to find an equation of motion that includes whatever it is we're trying to solve for, because otherwise, what are we doing with it? But we'd like to avoid any information we don't already have. So choose equations that avoid anything that's unknown that we don't actually want. So imagine if I had a problem where I was solving for the final position of an object, right? But I don't know where the object ends up, but I also maybe don't know what velocity it has at the end, right? I would need an equation of motion that would have to have the final position, which is x, but that could be this one, this one, this one. All three of those have x in it. However, if I don't know what final velocity I have, I wouldn't want to choose this equation because it's got the final velocity in it. I wouldn't want to choose this equation that's got final velocity in it. But this equation is missing the final velocity. So in that situation, this would be my friend. I would solve that equation and get the answer. And step 4, solve it. Do the math. Every problem in chapter 2 is going to break down to this same sort of process. And all we have to really master is, how do I implement those steps? That's it. Let's do an example. So for this one, I have a car that comes to a stop in an intersection. It was originally traveling (25 meters per second). That's about 55 miles per hour for those of you keeping score. But the skid marks are 30 meters long. What was the car's acceleration? Ran out of room there. Crap. So here's a big block of text where I've been told some stuff, and I need to implement this 4-step process. All right. Step 1, let's draw a picture and figure out what the heck's happening. I've got a car. So here is my crummy artistic rendering of a car. Now, that car originally was traveling 25 meters per second. So at some moment, here's my car, and he's got a velocity of 25 meters per second, and he's traveling to the right. But he's stopping. So what's happening is, as time goes on, he's going to the right, but I'm slowing down, I'm slowing down, I'm slowing down, I'm slowing down. And eventually